Oh my gosh. Hey guys, welcome back to Kitchen Table Chemistry, Tuesday, May 5th. And what we are going to do today is take a look at acid-base equilibria as we go through this whole idea of equilibrium. I'm going to do some background today on acids and bases because you did it last year, but maybe you're not 100% comfortable with it. And I would do this normally in your classroom, so let's do it now. We'll talk about what are acids and bases. We'll do some pH calculations, and we'll do eventually we'll get into Ka, Kb, and titrations. That's likely not going to be until a Thursday topic. All right. Characteristics of acids. What are acids anyway? Acids, anything with a pH below 7 is technically an acid, and we're talking about solutions. They will produce a hydrogen ion in water. They tend to neutralize a base. They are electrolytes. In other words, they conduct electricity in water. They have a sour or a tart taste. A lot of foods are acidic, and that tomato-based foods are acidic. They can be corrosive. In other words, they can oxidize metals, and that is a common thing that you'll see with acids and batteries. Okay, the strong acids. Strong acids are as follows: hydrochloric, hydrobromic, hydroiodic. And what is it that makes an acid strong? What we have is 100% dissociation in water. That's why they are strong. So we don't ever do equilibrium problems with strong acids because they're 100% dissociated in water. There's no reversible reaction. When you start with something like hydrochloric and you put it into water, it goes one-way arrow into hydrogen and chloride. So strong acids are like that. There's the first three. The other three would be sulfuric acid, nitric, and perchloric acid. So these six are strong. So anytime we're working with those, it's straight into a pH calculation. Anytime we're not working with those, we're working with a weak acid, we're going to be doing an equilibria. Now, the difference between a strong acid and a weak acid looks like this. Strong acids, we have this 100% ionization, whereas a weak acid, well, it starts at 100%. Eventually, it just hits equilibria here and will be much less than 100% in many, many cases. Looking at acid formulas, and I just thought I would throw this around, and that we've got these different acids. Of these, the four, perchloric is the strongest. The more of these oxygens that you have that are unbonded like that, the more that you have of those, the stronger the acid will be when we're talking about oxyacids. Characteristics of bases. Bases will have a pH above 7. They may contain hydroxides. All the strong ones do. They will neutralize an acid, and they have a bitter taste. When I say they'll neutralize an acid, they will tend to be able to absorb a hydrogen ion. They can absorb a hydrogen ion. They have a bitter taste. If you've ever had your mouth run out with soap, that's a bitter taste. That's a base. They are also electrolytes. They tend to have a slippery feel, and that I do not like getting strong bases on my hands, and it feels like your fingers dissolving. And they tend to be caustic, and that is in that they will also burn, much like an acid. They tend not to burn as quickly as acids do. Okay, the strong bases, you'll notice they have something in common. I'm just going to flick them all up at once. They are all hydroxides, and they're either hydroxides of the alkali metals or they are the lower hydroxides of the alkaline earth metals. And again, what makes them so strong is they will go from XOH, whichever one it is, and go to X plus and OH minus 100% in water. So those are the strong bases. The only base we really ever use is sodium hydroxide. We've used potassium hydroxide like twice this year, and that's it. Seriously, we've only really got a couple others back in the storeroom. Okay, where this all comes from is called Kw, the self-ionization of water. And if we take two waters, to a small extent, they are going to ionize with each other. So reversible arrow into H3O plus. This is called hydronium. And OH minus, which is hydroxide. So if we go to put this into a K equation, Kw for this would equal on the top H3O plus times OH minus over water squared. But wait, water is a liquid, and so we cross that off. So what Kw actually equals is the hydronium concentration times the hydroxide concentration, like thus. And that is the self-ionization constant of water. This has a value of 1.0 times 10 to the minus 14. And that is Kw, and it's no surprise that that is the extent of the pH scale, 14. Okay. This is just showing you the same effect. Again, even with my big head in the way of the two water molecules making us the hydronium here and the hydroxide over here. This would be H3O plus. It's water with another hydrogen on it, and this is the OH minus, the hydroxide. Okay. pH scale runs from 0 to 14. At 0, we have battery acid, and all the way up at 14, we have any sort of alkali type situations that we would use. What's at this would be sodium hydroxides, and that are up here. And drain cleaner, which be really careful with drain cleaner because it is like concentrated sodium hydroxide. So 0 to 14 with neutral in the middle. You'll notice down here we've got foods, and now things like lemon, and that I love lemon. And we've got soda, not so much for that. Tomatoes, again, awesome, but they are acidic little guys. Coffee, and that, so these are things. Water, which you should drink rather than soda, sitting right here in the neutral 7. Above things, by the way, your pH is a little above 7. It definitely is an 8 if you did, but it's a little bit above 7. And then eggs and other things, ammonia, and then the 11th, soaps are up in this area. Bleach, by the way, not a strong base, and not a strong base, and around 13, 12, 8. Okay. How do you calculate pH? pH is the negative log of the hydrogen ion concentration. So if you know the hydrogen ion concentration, you know the pH. So what is the pH of a 0.0118 molarity HCl solution? So pH here, and this will be our equation, is equal to the negative log. Why did it do that? pH is equal to negative log 0.0118. So we just want to take that molarity. Now, this is a strong acid, so I can just run its concentration right in there, and I would then get a pH value, which I get 1.93 as my pH. And that does make sense to me, okay? Why? Because we are 1, 2 on the exponent. So the pH is a logarithmic scale, and so the number of exponents will tend to come out to what the pH is. All right. Using pH to find the hydrogen ion concentration. So let's say we have something that has a pH equal to 4.5. What is the hydrogen ion concentration? We will use the inverse log and then negative pH. So in this case with 4.5, inverse log negative 4.5. And I'll just do that real quick on my calculator. Second log to get inverse log, negative 4.5, and I get 3.16 times 10 to the negative 5. So that means that my hydrogen ion concentration, or molarity, square brackets for molarity, is equal to 3.16 times 10 to the negative 5. Now, does this make sense to me? Yes. With a pH of 4.5, I'm going to get an exponent that's around 5, like that. So that does make sense. And that's how we go backwards. It is inverse log, and at a negative 4.5, you can practice it on your calculator. And at, let's go on. pH plus POH adds up to 14, easy. And so if you know the pH, you know the POH of something. And many times we'll be working with bases, so we will need to go and convert from one to the other, and they add up to 14, so it's a simple subtraction to find the one that you're missing. Okay, here's some examples. And again, I just wanted to practice this with you for a day. I thought it was a good skill. Now, pH and POH adds up to 14, so this would have to be 11.44. pH, to go back to the hydrogen ion concentration, what I want to do is take the inverse log of that negative pH. So take the inverse log of negative 2.56. And if you do that, you get 2.7 times 10 to the negative third. And again, with some examples here, you can make sure that you're doing it right. If we do that with the hydroxide, we get 3.6 times 10 to the negative 12. Now, the interesting thing is here, if you take the hydrogen ion concentration and multiply it by the hydroxide concentration, they should both equal somewhere around kW, 1.0 times 10. I knew that was going to happen. 1.0 times 10 to the minus 14. Okay. Here, now I've got the hydrogen ion concentration, so I want to go back and find the pH. So what I want to do is take the negative log of this. I want to treat it because this is molarity. This is hydrogen ion concentration. And I do that and get a value of, for this, 6.25. And let me just do that real quick. Negative log 5.63, second exponent, negative 6. 5.24. Who's lying here? I could tell it was 5.24. All right. Now let's just erase that. Done. We'll go to blue here for no good reason. Okay, so that's 5.24. 5.25. Now that means that here, this will have to be 8.75 because they have to add up to 14. And it means that my hydroxide concentration here will be the inverse or second log, inverse log of negative 8.75. And I get as an answer 1.8 times 10 to the negative 9. Good stuff. All right, if I only had the hydroxide concentration given to me, I'm still actually in pretty good shape, because what I'll do with that is use that to find the POH, and then from that I can find either the pH or the hydrogen ion concentration, depends on what I need. And so if I do that, I would come up with a POH of 4.55. And now I know that the pH would be 9.45. And the hydrogen ion concentration would be 3.55 times 10 to the negative 10. So this is how you can find all of this missing information if you only have one piece of the puzzle. By the way, acid or base always comes off of pH. So this is an acid because of its pH. This is an acid because of its pH, and this is a base. Above 7, automatically a base. Below 7, automatically an acid. That's how it functions. All right, I hope this and a little bit of practice and that will help make you more comfortable with this skill as we move forward. And I'm pretty sure it will. If not, you need to let me know. Tomorrow we're taking a quiz on the Le Chatelier's and this early ice chart idea. And I want to know if you're uncomfortable with that, please shoot me an email today so that I can adjust, or we can do a Zoom, or we can do some review and that, or what have you. All right, take care, and I hope you're having a fantastic Tuesday. Bye-bye.